So I hope now I am in the proper path, because now I am going to introduce a concept that actually is the keystone of Geant4, which is the concept of interface. So the concept of interface this is not only of Geant4 or C++, this is in general. An interface is a way in programming to explicitly declare what is the functionality that you want to have without having any functionality. In C++ in particular, there are many ways of achieving that. Geant4 back in the day chose to use virtual or abstract C++ classes that basically declare a class with a method that do not implement anything at all. And this is done to ensure the same functionality can be re-implemented in derived classes. But if the program is using an object that derives from that, this functionality should be provided by the user independently on the implementation. And we will see now an example and why this is important and why this is the keystone of Geant4. So if we open now if we go one level up with cd space ... and we open again with gedit the source code or application.cc, and we type enter. Actually, we can keep it, but will not be useful. In order to comment in C++, you can use // double slash, and like this will have no effect. So now we will start thinking about the concept of interface. Let's start with something very simple. We will start by declaring a class named cube. To declare a class in C++ is as simple as that. Class space, name of the class space, curly braces, semicolon. This class will implement something very simple that will be at the construction time. It will capture the size of the cube, and it will have a method to calculate the volume. To do so, we can define a constructor that is a special method that will be called whenever we want to instantiate this class. And we will store Geant4 double we can leave it simple for the moment. Good. In C++, by default, all the methods and members of a class, this will be called a method. Any function of a class will be called a method. Any variable of a class will be called a member. Everything is private, which means that it will not be accessible from outside. So if we want to make it public, we have to explicitly say that with the keyword public. And for example, the size of a cube, once we have started the cube, we might not want to make it public anymore. So we can say that that is private. In addition, we want to create the cube with a certain size when we create it. So we can say Geant4 double L. And we can declare already the size, some members of the class by doing this. This is read in the following manner. Cube will be the constructor. It will take one argument, which will be a Geant4 double, a double, name L, and the member f size will be initialized with the value of L at the moment of creation. We can do something like this now. And if we write in the main function cube space C and between parentheses a value, for example, 1.0, it will create a cube with size 1 unit. Sorry? F size. Yes, F size. Yes. Thank you. Well, you have to use one of the two. I don't know what is better. Let's keep it in F size. Whatever. Good. Now, if we want to implement a method that calculates the volume, we can do it like this. G4 double get volume, and the volume of a cube is F size cube. So like this. So for example, we could ask what is the volume, like this, and we could print it if we want. Okay. Now, what happens if we want to declare a class that instead of a cube is a sphere? So we will have to do something similar. So we will start by typing class sphere, open, close curly braces, semicolon. We will need to define a constructor that is public. So something similar to that. Again, we will pass by argument to the constructor the radius of the sphere, and we will initialize an internal member, f radius, with this value, and we will do nothing else. We have to define the internal member as G4 double f radius, okay? And let's define another function called get volume. If you remember the volume, well, if I remember myself correctly, the volume of a sphere is 4/3 multiplied by pi multiplied by the radius.
You've got a point too many.
Sorry?
Got a point too many. You do 4 by 0.3.
Good point. Thank you. Okay. We could do something similar. We could, that line is not doing anything. We can start a sphere with radius 2. And as we have the code now, you see that there is some similarity. There are some similarities now. And when coding, whenever you have redundant code, is a bad signal, and something should be done. Now you will see how error-prone this code can be. Imagine that we want to print volume. We want to declare a function that will print the volume of one of the sphere and the cube. To do so, it will be very simple in C++ to define a function. We have to declare first what is the type that it will return. It will not return anything. The main function, for example, can return int. That is the reason it starts by int. Then the name of the function, it will be called print volume. And then by argument, we can say, okay, print the volume of a cube. And then we can use G4 cout volume Okay. And what if we want to print the volume of a sphere instead of a cube? We will have to copy paste. We will be tempted to copy paste the code and do something like this. And again, you start to see some similarities that are pointing to some action to be taken. Now we have the same function that has two different implementations depending on the argument, depending if it is a cube or if it is a sphere. But actually, the action that is being taken is the same. We want to simply print the volume, but yet we have to implement the same function twice. We can put it here. We can say, well, after each class, actually. We can say print the volume of the cube, and we can say print the volume of the sphere. Okay. Has anyone not copied the code that we have been typing? Or okay.
The last part is remaining.
Okay, sorry. So the last part is the implementation of the print volume function that will print the volume. The first implementation of the print volume function will print out the volume of a cube. And then we have to almost copy paste the code. We only have to change the type of the argument instead of a cube of a sphere. And that's all. This was the only change. The implementation itself, you see that is the same. That is because we are only accessing a property of both classes that is common.
Thanks, Don.
Thank you. Everyone here in the room follow? Okay, good. We could try to compile. I will try to keep it in here, just in case. Sorry, I didn't open it with the ampersand. So this will be the last part. Now we can move to the build directory again, cd space build, and we can type make to remake it again. And we can execute our application, and it works as expected. Good. But what happens if we want to implement even a third mathematical solid? What happens if we have to implement more than 100 solids? We have to implement 100 times the same print volume function, one for each class. So this is the problem that interfaces solve. An interface would be an abstract class, so another class that we will call, for example, solid. Again, this is an abstract class, is not more than a class that will say, okay, I want a function that will be called getVolume, and any class that derives from this solid will have to give an implementation of this function. So it's some kind of promise that we are taking. Now, cube can derive from this class, which is pure virtual, because this class is not implementing anything at all. This class is only saying there will be a public method that will return a double, and this method is called getVolume, does nothing. It declares pure interface. And now cube will derive from this solid. Since getVolume actually is an implementation of the method that was promised to the base class, you have to mark this as override. This will not change the logic, but it will help us to spot problems in the future. The key word that we have to understand is virtual. Any function that is marked as virtual means that any derived class will be able to override it and implement whatever the class wants. In this case, cube will implement the function getVolume, but the function getVolume was promised to be implemented because it derives from this base class. Similarly, we can do the same with a sphere. So we say now that the class sphere actually derives from solid. It means that now it's taking the promise that the sphere class has to implement this getVolume method. We have to mark this method as override. Just this will not change the logic. It's just to spot errors in case there are. And now the print volume class that we have here, and we can comment out because we will re-implement something else. Instead of this, we can implement a new print volume class that will take as argument a solid and then actually we can copy the rest because the implementation is the same for everyone. Everyone managed to copy the code that we have so far? Yes. Maybe like this. I can actually erase this because we will not use it.
Is there a way to use some built-in pi function from Geant instead of writing 3.14?
Yeah, this is actually a very good question. So yes, Geant4 provides some constants and units, but I will review it just in the next step. Thank you very much for the question. Yeah, we will review how to access the constants provided by Geant4. Good.
Excuse me.
Yes.
Would it be possible if you quickly drop this code file into the Mattermost chat or something?
If I could copy, yes, sure.
Thank you.
Sorry. It's a bit tricky. Oh no. Sorry, this is a bug of the virtual machine in Linux. Sometimes I have to switch off and switch it again if I switch between the virtual machine and the master operative system.
This will be edited out in the.
I hope so.
What time?
Wonderful.
Sorry about that technical issue. We're restarting.
Thank you. So now we can go back. Sorry, I forgot to put a percent. We can go back to the build directory by doing cd space build. We can type make to rebuild the. Yeah, sorry, I forgot. Thank you. Is this better? Okay. So if we change directory to build and we do make to rebuild the application, we can now execute it again. We see that the functionality, the output is the same, but what changed is the code itself. Now we are simply declaring this class that will be the interface for Solid. Basically, it's saying that any Solid should implement a method called getVolume. The class itself is not implementing it, but any class that derives from Solid has to do it. If we don't do it, if, for example, we delete this and we try to compile, you don't have to do it, but I will do it for you to show the compilation error. It will happen. Okay. We have to understand this in the following manner. It's trying to derive, to make some internals because the class cube derives from Solid, but we didn't implement the method. It's missing completely. We can also comment it out. Now the error will be different. Now it's completely missing. Cannot declare cube as it is because the virtual double from Solid getVolume class function is not implemented. Okay. If, for example, what is this override method doing for us? Imagine that you misspell volume by this volume E, and we try to recompile. What is going to happen if we try to compile is that this function getVolume E is marked as override, as an implementation of a virtual method, but with override, but actually it's not overriding. This override keyword does not change the logic, but it will help to spot errors very soon. Any questions so far?
Can you maybe share the make file on Mattermost as well?
Sure. Good point. Thank you.
It's not visible to remote people anymore. I don't know what you managed to get into. You're in Mattermost. Sorry, you're showing by Mattermost.
No, this is just a.
So we're working with V1 again. I thought
we have we have copy pasted the CMake list from the example basic V1, and we have changed just the last 3 lines. So instead of compiling the example V1, we are compiling actually our application. So I posted in the Mattermost the source code that we have just implemented, the CMake list and the instructions to compile. You don't have to worry about this because in the GitHub repository of the course, you have this intermediate or preliminary code available for you, so you can play with it whenever you want. Okay, so just for takeaway home, the concept of an interface is just a way in programming to declare what is the functionality to be implemented without implementing it. Sometimes might be a dummy implementation, and the implementation itself will be done in the derived classes, as we have seen in this example with the cube and the sphere. Geant4 will exploit this because Geant4 does not care how your detector looks like. Geant4 only cares that there is a volume, and the volume has certain methods, and Geant4 will interrogate those methods. But what is the implementation of those methods? Geant4 does not care. Geant4 implements more than 100 solids, including the second-order surface solids, and all of them will have a common set of functions that will be used to navigate the geometry during the simulation. But the implementation solid by solid is not important when doing the simulation itself. It's only important to know is the distance to the border, to the one face of a solid, or how much is the volume of that solid, but how this is implemented for each solid doesn't matter. And we will see this concept of interface not only for the geometry, but for many other things. And this also makes Geant4 very powerful, because if you want to extend its functionality, you can always take, or in many cases, you will be able to take some of the Geant4 interfaces and implement your custom solid or physics process or particle or whatever you want to add to Geant4 toolkit. Good. Any questions so far? Good. So now John already left. Oh. So Gabriele, I would like to maybe now write on the blackboard. Should we change the camera, or I mean, I can use that one or the main one? What do you? It will be better that one. Okay, so we can go there. Fair enough. I think I was trapped. I am still in the Zoom session, but I log out. Ah, perfect. I think tomorrow I can try here. It will be a pity I will try to write in big letters. Otherwise, we should check that. Anyhow. Now we can start introducing the Geant4 components. This is the. Okay. Well. I think it didn't change the camera. Yes, it was, but this is the camera of the laptop.
Oh.
Ah, but we are sharing the proper.
Yes, yes.
Okay, okay. Good. It's a bit disturbing that the video point is this. It's okay. It's okay. No, it's okay. We are sharing the proper angle, so it's good. So we have just reviewed the concept of interface that will be used by us to let Geant4 know the description of our custom problem. Now I will introduce the minimal components that we have to define in order to run a Geant4 simulation. The first one is the most obvious one. So when you are doing an experiment, you have usually you are doing the experiment or whatever experience you are doing in a room. Inside the room, you have tables, you have chairs, maybe humans, if you are in medical science, in medical research. If you are doing nuclear physics or high energy physics, usually you have a detector that is not alive, and inside the detector, you may have some components. In case we are here in a room, we have tables, we have laptops. Inside the laptop, we have other components. But we are sharing this one or that one? Oh, unfortunate. So the geometry, or it seems kind of obvious that the first component that we have to provide to Geant4 to run a simulation is the geometry and the detector description, the setup, a description of what we want to simulate. It can include a room, it can include the tables, it can include a human with internal organs. So you have already an idea, a native idea of what you want to describe. You need a geometry, a hierarchical geometry. You have a room. Inside the room, you will place people. Inside the people, you have organs. Each shape, mathematical shape, will have each volume will have a given material. So you need to provide materials that will be used by Geant4, and you have to provide also a certain geometry. To do so, we will use a Geant4 interface called G4B user detector construction, and we will have to provide the materials and the geometry in a method called construct. And in a similar manner as we have been doing so far with the solid and get volume, we will have to derive our own detector constructor or geometry constructor, as you want to call it. And in this method called construct, we will declare there a list of materials and geometry. And this is the way Geant4 will know or will use how our geometry looks like. Geant4 does not care how we implement this method. It's our responsibility to provide a method that will build some geometry, but Geant4, as it is, does not care. It will build whatever we want. So the first component, so I will do here a map of what is we have in reality and what is the Geant4 component. So in reality, we have some geometry. Here we will have G4B user detector construct. Next thing, when you are doing an experiment, the next thing you need to understand before doing the experiment is the physics and the particles that may happen during your experiment. For example, if some particles are being created, you need maybe to understand, are those electrons? We know the mass of the electron. Yes, we know. Okay, we have to tell Geant4, okay, in my simulation, some electrons may happen, some gamma rays may happen, whatever particle you want to happen in the simulation, you need to let Geant4 know. And similarly for physics. So if I want an electron to be simulated, an electron will interact with matter in a certain manner. So we have to provide a list of processes that will be attached to this particle and will tell Geant4 how this particle interacts with the matter of the geometry. that we just developed. To do so, we will need to derive from another class, user physics list. We don't care at the moment. We will implement our detector constructor. We will not implement the physics list because it's extremely complicated and error prone. And also Geant4 for many years now provides some ready to use physics list, reference physics list that we can use out of the box. And this is what we will use. The third component that is needed to run a simulation is what are the particles that will interact with in our setup and that will define the event. Those are the so-called primary particles. As I said at the very beginning, Geant4 is not a primary particle generator. In high energy physics, there are dedicated programs for that. In nuclear physics, if we are studying a radioactive source, Geant4 provides a radioactive decay module that we can use. But if this radioactive source has some spatial dependency or some features, maybe it's the Geant4 components are not enough to describe this, and we have to define ourselves how the radioactive decay looks like. In case of medical physics, we will need to maybe to define an extended an emission point or primary particles that is coming from an organ or something like that. And in case of space applied sciences, we may need to model, for example, cosmic rays. And again, we need to provide what are those cosmic rays, what is the energy spectrum of those, what is the particle cocktail, where are they coming from? Are they coming from a point or from a bigger area? So all of this Geant4 do not provide. It's our responsibility to tell Geant4 how these primary particles are injected into the simulation. To do so, we have to override another class called G4B primary particle action. These are the three main components that we will implement on Wednesday, and we will allow us to run a Geant4 simulation silently without extracting any data out of this. There are other actions that are there are other interaction points that will allow to extract this information. Those will be optional user actions. Sorry, here I forgot to put user. Anyhow, and this collection of user actions will have to be also declared to Geant4. But the important thing is to map this at least until Wednesday. Good. So, and yes. G4B user primary generator action. Yes, thank you. Hopefully at the end of this course, I could share with you the document where you will have basically all the material with the code and the content of what I am speaking of. Geant4 is Geant4 provides a number of classes, objects. There is only there are different types of objects, of classes. Sorry, there are a special type called manager. This will give you access. Those are so-called singletons. That means that there is only one instance of that class per simulation, and there is only one manager that the user has to create in order to start up a simulation. That is the so-called G4 run manager. We don't have to override that, but we have to use it. And it's a pity that this screen is so small. We have to register we have to register the geometry into this singleton. We have to register the physics into this singleton. And the user actions, so-called user actions, they are registered in an intermediate class called user action initialization. Not only this one, but and this user action initialization is the one that will be registered into the run manager. Okay. These 4 classes are the only ones that are mandatory to run a Geant4 simulation. And we will see the other ones that are optional, but very useful to extract simulation on Thursday. Any questions so far? Yes.
Sorry, just I couldn't get what's the role of these run managers. So,
Yep. Thank you.
what it's doing.
The simple answer is it's a bucket in which you put all of these things. That's the first answer.
Thank you. No, the run manager is an object provided by Geant4, and we will use it just to register the geometry, the detector setup, or whatever setup, because actually it does not have to be a setup. Whatever geometry we want to simulate, we will register the physics, understanding by physics the collection of particles and processes attached to these particles. And we will register a collection of user actions. The only user action that is mandatory for running a simulation is the action that tells Geant4 how to start up a simulation, how to start an event, how to inject primary particles into this geometry. And that is the so-called G4V user primary action, primary generator action. Primary generator action, yes.
You want a bigger blackboard?
Yeah, I was not sure if we could use it because the camera was not pointing here and we didn't configure it now.
If you want to use it, I'll configure the camera.
Thank you. Sorry, in principle, we were expected to be using the big one. Okay. Similarly, as the run manager is a bucket where we put these 3 components, the user action initialization is just another bucket where we will put all the user actions. The only mandatory user action is the one that declares how explains Geant4 how to inject primary particles, but there are others that we will review on Thursday. Thank you. Any other question?
Would you please give an example of primary user actions? For example, any one?
So this is the base class from which we will have to derive or own. This base class, again, has a virtual method called generate event, if I remember correctly. And in this implementation, in our implementation of this method, of this virtual method, is how we will tell Geant4 how to generate primary particles.
Okay, get it. Thanks.
Basically, in this method, you will see on Wednesday is how we will tell what are the primary generators. In our case, in our application, will be an electron going in a fixed direction with a fixed energy. So at the beginning of each event, we will be generating that. Does it work? It would be wonderful if it works. Sure. And actually, that question brings me to sketching a bit how what are the main simulation steps for Geant4. Okay, otherwise I can simply reuse this screen. As I said, before running a simulation, we have to register to the Geant4. We have to let the Geant4 know what is our experimental setup or the list of materials and geometry. We have to let Geant4 know about the list of particles and processes that will be happening or can happen during our simulation. And then we can start the simulation itself. A simulation starts by starting a run. And a run is a collection of events. An event is okay, thank you.
The camera a little bit further.
Thank you. An event is defined by or it starts with certain primary particles being injected into our geometry. In our case, our geometry will be a box inside a wall. Imagine that this is the room where we are. We will be injecting a primary particle, so an event can start. We can inject a primary particle from this point, and then Geant4 will decide what to do next. We cannot, once the simulation starts, we cannot change neither the geometry description, neither the physics. And Geant4 will use the processes attached to this particle to decide what is happening next. Using some of these optional user actions I just mentioned before, we can know after each step or after each event what happened, but during the simulation itself, we cannot change it. So at this point, it will cross the boundary of this other material, whatever it is, we don't care. It can make another step. Along the step, it can deposit some energy depending on the processes attached to this particle. If this is an electron, it can create some ionization along the way. At this point, also maybe create some secondary, whatever it is, and the particle will keep traveling until certain conditions will declare this, will kill this particle. These conditions can be that it does not have more energy, so all the energy was deposited along the way. It decayed in case it is an unstable particle. It can be killed by some user actions, etc., or it can be annihilated in case of a positron. Along the way, some secondary particles can be created, and Geant4 will track all of them. Once all the particles that were injected at the beginning of an event, plus all the secondary tracks that were being created along the way, are tracked fully until this end of track condition is fulfilled. Once this is achieved, the event is finished, and a new event will start. For Geant4, this means that it will be like nothing happened. And then, or generate event, generate vertex, I don't remember exactly what is the name of the method now. It will generate again, in our case of our application, it will generate again another electron with the same direction, energy, and it will be injected, and another simulated event will happen again until all the primary particle and all the secondaries that might be created are tracked. And this will define a second event. A run will finish when all the events are simulated, and we can choose how many events in the run we simulate. When we were clicking on the green button, when we were using the Qt interface before with the example, it was simulating one single event, but we can simulate many events in one run. Any questions so far? Yes.
One second.
I'm sorry.
Yes, thank you. There you go. I think you mentioned it, but I'm not sure to have understood it. Do you have to give the direction of your primary particle as an input?
Yeah, thank you. That is a good question. We will see more details on Wednesday when we implement our primary generator. But yes, basically, when you inject a primary particle, you have to give a minimal information about that particle. So the particle type, Geant4 already knows about some of the particles. Geant4 already knows what is an electron, but still you have to tell Geant4, please use an electron. And then when you want to use an electron as primary particle, you have to say, okay, I want an electron moving into that direction. It can be a rest. Maybe you want to inject, for example, a positron, and you only want to see how it is annihilated with time, because it will be annihilated at some moment. And in principle, that would be all. But yes, if you want to inject, for example, a radioactive ion, you have to give a bit more information. For example, if it is a radioactive ion, maybe it's an isomeric state, or maybe it's in the ground state, or maybe it's moving, maybe it's not, depending on how you want. Yes, thank you. I think, John, there are other questions.
If
So
in my concept of an event, there are the generator will give us many particles, which we then pass to Geant4. Is the tracking of each primary particle an event, or can an event have more than one primary particle?
Thank you very much for your question, because actually it's very interesting. Yes, an event is defined by the injecting one or more primary particles. We may have several. For example, I don't know, typically in high energy physics, we may have, if we omit before the collision, we may have thousands of primary particles starting from the center of our detector. And all of them will still be considered primary particles. And Geant4 will have to track for one single event, all of them, plus all the secondaries attached to those, or that those will generate, sorry.
So
can you introduce the external forces, for example, a magnetic field? External forces.
Yes, you can have an external electromagnetic field, and Geant4 will take care of it so long as you're able to describe it fully. It's up to you to describe the magnetic field, but Geant4 will derive, you will tell it that there's a magnetic field, you will provide it, and Geant4 will handle it. Yes, and I've written it. I've written the classes that deal with the magnetic field. So there's a question that's remote, so please go ahead and ask your remote question.
Yeah, thanks. So my question is, since you said it might know the electron exists, so the kind of interaction a particle can undergo, it also already knows, like for example, whether it has to produce a secondary vortex or not. So, or we have to provide this information.
Okay, we will be using a reference physics list, and everything will be already contained in that object. And if you want to know more about the processes or models that are used for each particle, please take the advanced course, because actually to answer properly this question, it goes a bit beyond the scope of this course.
Okay, I still have a question. Where in the stack does Geant4 sit? Like if we have whatever initial vertex generating, I don't know how many particles, consider, I don't know, proton-proton collisions, where does it sit? Like, does it do the initial collision, or does it like?
That is, yeah, thank you for your question. Actually, that is very interesting. Usually because in high energy physics, the particle physics events are so complex, this task is delegated to a dedicated program, usually PTI, ERVIC, or others. And then the output these programs generate is injected into the Geant4, because Geant4 in principle is not a realistic primary generator. It can simulate a reductive decay because it has the information to do so, but it might not have enough information with enough detail, with enough accuracy. But maybe John or Gabriele can complement.
It depends on the energy scale. And if you go into hundreds of GeV, you might have something that's more accurate, and certainly TeV and up. And anyway, it also depends on your requirements. The LHC experiments have very precise requirements for event generators. If you have just a beam with a Gaussian spread in position and energy and direction, then you could write your code yourself, or you could find a module in Geant4 that does something similar.
But in principle, for example, in this case, doing a proton-proton collision with Geant4 could be an overkill, because we will have to simulate 1 billion protons against 1 billion protons, and Geant4 will have to track.
No. We're talking about one proton on one proton.
Oh, one proton. Okay.
Or one proton on hydrogen target, Geant4 can handle up to most energies.
But this is another thing I didn't mention. So for each particle that Geant4 is simulating, Geant4 forget about the other particles. The simulation for the tracking for each particle is done in a clean environment. When an electron is being simulated, for example, this, whatever, this, and if along the way other secondary particles are being generated, during the simulation of this proton, those secondary electrons is like they don't exist. They are put away, and only once the tracking of the electron finish, Geant4 does like this, and starts the tracking of the secondary electron from wherever it started, like this, like this, like this. Once the secondary electron is tracked until the end, it will take the next secondary particle from here, here, here. It means that Geant4 do not remember which particles are being tracked. there is no memory effect. The simulation is assumed to be particle tracking independent. The tracking of each particle is done independently without memory effects. If I am correct, maybe John can. Okay.
There's a general assumption of all particle transport tools and toolkits that is the case. Otherwise, the simulation becomes much more complicated. There are side cases, but all the general tools, kits, and tools, Geant4, Fluka, MCNP, EGS NRC, EGS4, all of those toolkits assume that each of the initial particles and each of the secondaries are independent of each other.
Okay. This is a general assumption, doesn't mean that it's correct. It means it's an assumption. Sometimes it will be correct. There might be cases it is not. And it's user responsibility to validate if this assumption is correct by doing the validation. Geant4 is not validated by itself. There are some models that are based on some ethical. Geant4 implements some models that might be more or less accurate, but at the end of the day, it's responsibility of the user to validate the simulation itself, the application.
So let's just be realistic. When will it break down? If you have so many charged particles inside your gas detector and right near your wire, the field is too large and it creates a cascade and it burns that, Geant4 is not going to simulate something like that. You have to figure out that there's a discharge is going to happen and you're going to, this will not work anymore. That's an extreme case, but that's the sort of case where what happened before has affected your setup. Or if you're simulating a beam dump and you've discharged enough particles into it, which would be a bit shocking to be able to simulate them, to heat it up by 1,000 degrees, it will have melted. It will no longer be. If it was a liquid beam dump, it might have turned all into a into gas. These effects have to be simulated outside of a Geant4 simulation. Most other effects are much more minor. The timescales upon which these interactions happen is very short compared to most of other things. So this is a very good assumption.
There is a question on Zoom. So can we put a radioactive material with specific activity and simulate in Geant4?
Come back for the advanced course.
Okay.
Another question. Can be used to simulate radiation interaction and energy deposition in electronic circuit and electronic components. For example, effects in semiconductors, detectors, or spacecraft electronics.
Simple answer is yes. The details require another half a week to a week.
Okay. Is there any other question?
Yeah.
Yes, for the advanced course. So is this already planned?
October or early November, I think is probably it.
Okay, thanks.
Okay. If there are no other questions, maybe we can start. Yeah? Okay, so we can start already. Yes.
I have a doubt. May I ask one question?
If you have an extra question, please go ahead.
For example, in our primary source is gamma radiation, and in gamma photopeak, we get the most of the particles due to primary events. Is there any way so we can find out all the events that are in photopeak are from the primary events or secondary events or multiple events?
I'm sorry, we could not quite hear you. Could you write your question down in Mattermost,
okay.
preferably? Zoom otherwise?
Okay.
Okay, there are no other questions? Okay, good. So now we can start already introducing or writing down our application. today it's a bit tight, so we will just review how to implement the materials. Tomorrow we will start implementing the geometry, and as a second, basically by overriding this construct method of the base class of Geant4. With that, we will have the detector construction. The physics, we will take whatever Geant4 gives us reference. And finally, we will need to implement a primary generator. This will be done between today and Wednesday. Okay, so now I will start a short presentation about how to build the materials in Geant4, because it can be a bit granular, and also it gives a chance to review some basic concepts. Okay. So as I said, for describing our experimental setup, we need to provide a list of materials and the geometry that will link the materials to mathematical shapes placed in a space. The Geant4 material model, here now we will review the Geant4 material model, the material, how to define a custom material, and finally how to access predefined materials, because many of the materials that we used in a simulation problem are very common, and there are reference materials. The second part of the geometry definition, we will leave it for tomorrow. So the Geant4 material model follows the natural one. The materials are made of elements, and sorry, better, yes. So materials are made of elements. Elements are made of isotopes. There are three main classes that Geant4 provides to describe this. The G4 isotope that describes the properties of an isotope, basically the atomic number and number of nucleons. And well, it has a unique name, and Geant4 will assign it a unique ID. The nuclear properties, for example, would be associated to this. A G4 element describes the properties of chemical elements with and they are characterized by an effective atomic number and number of nucleons. And they should have also a unique name, symbol, and Geant4 will provide an index. For example, the atomic properties will be attached or associated to this G4 element. And finally, G4 material describes the macroscopic properties of matter. So like density, state, temperature, with a unique name. G4 material is made of elements. G4 element is made of isotopes. The material density must be over 0, and it should be configured except for if using the predefined NIST materials. The temperature and pressure can be optionally set. Otherwise, the natural units are used. The natural properties are used. The material state is assumed always to be solid, except the density. If the density is below a certain threshold, Geant4 will assume it is gas, or if you explicitly say so. The materials are assumed to be isotropic and not so. By default, it does not contain any information about the crystalline structure. However, Geant4 provides in the later versions ways to include some effects such as channeling. And as I said, one can always use the Geant4 classes to define custom materials, but also we can use the predefined NIST material database with predefined composition and properties. And we can also take a look to the documentation about this. We can define an element like this. If we define an element without saying the isotopes, Geant4 will assume it is the isotopic composition will be the natural one. But of course, we can also change the isotopical composition by defining the isotopes, and then using the method add isotope to a custom element, we can change the proportion. In this case, you have the example for uranium. So this will represent enriched uranium. And finally, to define a material, if we want a material made of one single element, we can say simply the atomic number, and Geant4 will look for the corresponding atomic number of the element and will make this material made of 100% this element. But again, Geant4 allows us to define a material made of different elements. And there are two ways of defining the composition. Either by stoichiometry, so it means that we can give the ratio of atoms, and Geant4, based on this ratio, how many atoms with one respect to another, and what is the density of the material, will calculate the final atomic density, how many atoms per volume there are. And the alternative is to provide the composition of the G4 material by fraction of mass. In this case, you have the example of air, and you have here the air is defined with 70% nitrogen, which is an element that should be defined before. The code is not shown here, and 30% oxygen. And similarly, we can also, instead of making a material out of pure elements, before we were doing air out of nitrogen, pure nitrogen and oxygen, or water out of pure hydrogen and oxygen, we can also mix a G4 material with another G4 material. In this case, we have the aerogel, which is a material based on silicon, but it also has some water and carbon, and you can also add air as another material. And G4 material have these methods to do so: add material to add a new material to the definition, or we can also add pure elements if we want. At the end of the day, it doesn't matter. Geant4 will consider the material as a collection of atoms, and the interaction of the particle will happen with a single atom. There are, by default, no molecular effects, no solid effects. The interaction of the particle will happen with one single atom. Okay. Sorry? Yes. So it doesn't matter how you define the mixtures. If you define it as mix of materials, a material plus elements, made of elements, at the end, doesn't matter, because Geant4 will say, okay, how many atoms I may find along the way, and what is the probability? The probability will be given by the amount of atoms it will find, and then the interaction will happen with a single atom. But there are no molecular effects. So the particle will not see a molecule. There are no molecular effects included. And for example, ionization in solids is a very complex process. In Geant4 is captured in a gross manner, but there are no the full chain of how ionization actually works in reality is not implemented in Geant4. It's calculated in a gross manner and taken into account like that, but not atom by atom or including the solid properties. Yes.
I'm a bit confused by the system of units that I see here. So this density is given as a mass per area, and previously was given as mass per volume.
Yes.
Does it infer what to do? Or?
Yeah, this is actually a very good question. So units are always confusing, but we will review it the first thing when going on the hands-on part of this, or after the presentation. We will be using the unit system provided by CLHEP. Unfortunately, there are many unit systems in nuclear and high energy physics. I guess in medical science or space science, it can be even more, because each framework will define their own. Root and Geant4 units do not match. So whenever you want to use both in the same framework, because whatever reason you need to, you have to pay extra attention to it. I will go into more details about what are the units or how to deal with them later. And finally, so far we have reviewed how to do it, how to implement our materials by defining our elements, even or isotopic ratio if we want. But if we want to use, for example, a predefined material, we can use the Geant4 NIST manager, which is just an internal database of Geant4 that can provide elemental or material properties. And it basically, we can retrieve a material with all the standard properties. And this is actually the preferred way because it can ensure reproducibility of the application. And at least if you use this internal material database provided by Geant4, someone in Geant4 has taken the effort and care of ensuring that the properties are correct. And we will see the difference between using a material from the NIST manager or defining our own, because there will be properties that will be different. The materials are grouped by topic, but we can also retrieve them directly by name. We will see in the documentation what are the materials. Yeah, sorry.
The question is if you define predefined, if you use the predefined materials, can you still change them?
Yes. So the question was if we can still change properties of materials retrieved from the NIST manager, and yes, the answer a priori is yes, you can always change it.
So if you take a material and then change its properties, then and keep the same name, you're setting yourself up for problems in the future. I recall 20 years ago, one experiment which shall remain nameless, who'd taken the code of Geant4, changed it because they had found a bug. And then 3 years later, they were telling us that the program didn't work. They had an issue with this particular thing. So it is rather dangerous. It's better generally to copy something, rename it, that it's adapted, and move on from there, or create it from scratch for yourself.
Thank you. We will see what is the naming of these elements provided by the NIST database of Geant4, but all of them, as you can see from this slide, all of them will start with capital G4 underscore and the name of the element in case of an element, or G4 underscore the name of material. How to access the NIST manager, we will see on the hands-on session. And well, as I said before, for our application, we will be using this manager, as John said also, to ensure that we will have all the same material with the same properties, and just to avoid problems in the future. Any questions so far? Okay. Otherwise, we can jump to the hands-on session, so we can start already our application.
Alvaro,
yes.
You did not put the PDFs of your slides yet on the timetable. I think
I uploaded them and I noticed that they were empty. Sorry.
So we will have to take care of that once the lectures are over, so people can refer to the slides.
Yes. Thank you.
I have added the link to the GitHub. All material is there. So I mean, you can retrieve the slides from the GitHub.
Okay. So we can start our application. To do so, we will open a terminal. I will increase the size if I can. Well, okay. Okay. We will go to our work directory. Yes. Yes.
No, you just said it's too small.
It's a recurrent issue. Yes.
Could we show the timetable and show where a link to the GitHub material is?
Sure.
So people who want to look at the slides can access it already.
So I will show you where to find the slides and the rest of the material. So this is the Indico web page.
Going to the timetable.
Timetable, okay.
Gabriel has added a link to the GitHub page.
Ah, perfect. So if you click here in the clip, I can make it even bigger. So if you click here, it will someday redirect you to the GitHub project of Mihaly Novak, and in particular to the directory where you can find the slides. We have been reviewing the introduction and the detector construction.pdf, only the first part.
Thank you.
Thank you. Good. So at this point, we are ready to install to start. We can keep modifying this file. Or no, better, we will start a new one. Sorry, intro to. We will create a new directory called intro to Geant4. We can copy the CMakeList file from intro to C++ to intro to Geant4. Ah, sorry, I forgot. We can copy the CMakeList from intro to CPP. So we type cp space intro to CPP and slash CMakeList to intro to Geant4 like this. Good. We go to intro to Geant4 directory by typing cd space intro to Geant4. And we type gedit or application.cc as before. So we can reuse exactly the same CMakeList. We are simply doing this to keep it more clean. Okay. We will have to define a new main function because we are starting from scratch again. So as we were doing before, we have to include the headers that we need.
Excuse me, can you just show the terminal again, please?
I'm sorry, I was too fast. I can keep it up. In which point?
Here it is.
Okay, okay. So we just copy pasted the CMakeList from the intro to CPP directory to intro to Geant4 directory. We moved into the intro to Geant4 directory by typing cd space intro to Geant4. And now we open the file that do not exist yet. Gedit space or application.cc ampersand as before. The file is empty because it does not exist yet. And now we can start typing the following. First, we will include G4 isotope.chh. And if the question was if we have to include global, we can if we want to use the types of Geant4 and the EOS, the input-output streaming. We can do it. It's not harmful at this point. Thank you. And now we can start implementing our own G4 isotope object. Now, how to create an object of this type? Well, a priori, when you don't know, you have to check the documentation. So We can go to the user guide for application developers. We can click here in HTML. Okay. On the left menu, we can put G4 isotope, and we will find all the references to it. In the documentation, you can see a very brief reference to this. This class only describes the properties of atoms, okay, what I told you before, but still does not tell you much how to create an object.
Where do I get into this overview?
The overview, this?
Where are you?
Sorry. Yeah.
I searched there.
Yes, I searched on the left. So after going into the for application developers guide, this is the guide that we will be checking most of the time. Yes, sorry. We can go to HTML, but you can download it also in PDF. And here we can put G4 isotope, and we can look for it. In our case, the first place is already with one. And here you can find the reference. This is not telling much. This is not telling much about how to build an object. So we can go to the GitHub page of Geant4. That will be github.com/Geant4/Geant4. And you can look for this file. You can also find it in the source code that, in the installation directory, and it should be the same. So here you can see that the class G4 isotope has only one constructor, and we have to provide these arguments. The last two have already a predefined value, so those are optional, and Geant4 will calculate them in case it is needed. So basically, we have to provide the name, the atomic number, and the number of nucleons. Okay. To do so, we can go here, and we can create G4. We can go back to the source code, to the main function. And we can create a pointer. Okay.
Is it ISO 12?
Thank you. Yes. Sorry, there was a mistake. We can define the name of the variable that I wrote is ISO 12C. So in the first line, we are creating a pointer G4 type G4 isotope, and we are initializing the pointer to a new object G4 isotope. The symbol will be C12. The atomic number will be 6, and the number of nucleons will be 12. Then, because the class G4 isotope can have a method, a way to printing out in the terminal, we can redirect to G4 cout directly the pointer, and we will see what happens. Is everyone in this point? Good. I will keep it open just on the top. Good. Sorry? I cannot hear. Sorry? Yes. So now we will go to the terminal. there is nothing in the directory intro to Geant4. We should have only our application.cc with this code that it's been not shown. Why it's not shown? I have not been sharing?
It just stopped sharing a second ago. You were sharing before.
Sorry, my Zoom process hung out. Okay, so we just typed this code that will create an isotope of carbon by using this syntax, and then we will print, well, we will redirect it to the output and see what happens. Again, to compile, to configure the project and to compile, we will use CMake space -s dot -V build. I will keep it up. So CMake like this. Okay. Sorry? Ah. There are always errors. Now we can move to the build directory and do make. Everything good. Okay. If we execute, now we will be able to print some information. As you see, the molar mass was calculated by Geant4 automatically. If you put different element, it will have different value, and it will recalculate according to the internal information that Geant4 knows. Yeah, sorry. Please no. Okay. Okay. So we could do okay, this is an isotope. We could play the same game with element. So for example, you will never guess how to do it. Element C 6, and at this point we will need to review what units are. And where they live. Okay. Remember to include so we have, if we want to define a custom element, we have to include the corresponding header before the main function. And then you have to define a new element as this, G4 element asterisk LC equal new G4 element, and then we have to provide the symbol, the effective atomic number, the molar mass, and then we can print it. Okay, we can try to compile by going back to the terminal, type in make. We see that a new error happened. So it says that CLHEP has not been defined yet. It means that the units are not included in these headers. The units of Geant4 are in another header called system of units. we recompile now, yes, because I forgot. Then first we have to provide the name, but we have also to provide the symbol. Otherwise, the error message is horrible. Okay. So the arguments, we didn't check the header of G4 element, and that was the reason of the mistake. The constructor of G4 element takes the name of the element, the symbol, the effective atomic number, and the molar mass. And now we will review the units. But first, let's try it out. I can make it bigger because otherwise this is okay, better. Okay, so now we see that element carbon was made according to Geant4 has these isotopes. It could find the isotopes because we provided the atomic number. The atomic number will be used internally to derive what is the element, the actual element that we want to define, and Geant4 will fill the isotopes as we need. And you see that it is respecting the molar mass that we are providing. Now, the question of units is very simple, but at the same time, very easy to do a mistake. The first thing that you see here is the code. It's bad for several reasons. The first thing is that when we are providing the names and the numbers, we don't know what are these numbers for. One way to improve it, if you go to the examples of Geant4, would be to define some variables at the top and then assign it here. For example, something like that will give you already more information. You can also add yes, because this is not Python. This is just a trick to improve readability, but actually is a bit misleading. You can also inline a comment like this, just to make clear that this number is actually the number of nucleons. You can use more verbose variables, because otherwise it will be misleading. Okay. I will leave it as it is. Yes.
This might be confusing since the argument should be integers, not doubles in the case of isotope.
Yes. That is true.
Except for A, which should be a double.
Yes. This A should be integer, right?
No, A should be a double.
Ah, okay, sorry.
What's the reasoning behind that?
Isotopes with Z and N have to be integers.
Okay.
Just a question. Why is like the
choices.
So the question was why G4 string actually is capitalized while the other types are not.
But for one thing, int and G4 int have to be as close as possible. Similarly for double and G4 double. The rest are arbitrary.
Okay. Sorry? Yes. We will use it, for example, for element. Again, this is just a trick to make the code a bit more clear while it is still compact.
Here it needs an N as well. Which was
lost. Okay, you can use N. Still, this, as a good practice, you should never use variables made of one single letter. It's extremely confusing and very error prone. You should use more verbose, still compact. You have to choose depending on the application. I will try to make everything very verbose. This is the code can become very big, so I was trying to use this intermediate solution. We will see when implementing our application, we will have to use a bit longer names for our own understanding. Okay. Good. So this will be already a bit better. Ideally, you should put the numbers, you should initialize the variables before and then use them by value as they are. But in this case, we will make an exception. But we have to know that this is bad practice or not the best practice. And finally, we will arrive to the unit system. So the units are provided by CLHEP. There is a file in user local CLHEP include CLHEP. You see that there are many utilities. There is a directory called units. There is no need, you have to go there, but if you want. And here you see that we have a global system of units, sorry, and we have some physical constants. You don't have to dig this deep. This is just to show you what are the natural units of Geant4. So the natural units are these ones. Geant4 units are the millimeter, the nanosecond, and the mega electron volt, and the other ones. And if you go to the implementation, what you will see is something like this. There is a variable called millimeter that equals 1. It's as simple as that. And when we want to, we don't care what is the millimeter. We only have to use these names, millimeter or meter or whatever. Geant4 will take care of the implementation of all the units for us. What is important for us is that when we use a value with units, we have to provide the units. In this case, grams per mole. Because otherwise, you will be providing a number to Geant4 that will be reinterpreted assuming these were the natural units, and it might not be the case. So very important always to explicitly say the units. Okay. And the other way around, when you ask Geant4 for a value, for example, when you ask Geant4 what was the energy deposit, if you want the energy in certain units, you have to divide by that magnitude, by that unit. If you want the energy in mega electron volt unit, you have to divide by CLHEP mega electron volt. Good. Any questions so far? Okay. No. This you can specify the name of the variable outside. For example, you could say this would be more verbose and more correct. The problem is that I would need to type more. I just wanted to go a bit faster because we have only 20 minutes left and I wanted to cover a bit more the topics. Okay. We can also define another isotope. For example, carbon-13 by just copy pasting. There is not much to copy paste. So we copy paste the line before, ISO 12, C, and we rename the name of the element, the isotope, sorry, as ISO 13. We have to change the symbol. So now it will be C13. And now we change also the number of nucleons to 13. Good. Now we can define a new carbon, actually. I don't know. Prehistorical. custom carbon element. Oh, we? Okay, let's try to compile. So it was not integer, it was a double. So, sorry.
I think it's your molar mass because it's string for you.
Yes. So here we change the type. We can keep it as double. And if we go to build and remake,
Molar mass.
give me a second, please.
Molar mass should be double when you use string.
Sorry. Yes, correct. Yes. The molar mass should not be a string. No, should be a number. Yes. And if we execute it now, it should be correct. Yes. Thank you. So we can define now a custom carbon, and we will define our element as made of two isotopes, and we will use the isotopes that we just prepared before, and we will assign it to it. Okay. To add the isotopes, we have to use the method add isotope, and we can simply call the name of the variable that we assigned before. And we have also to assign an abundance. So inside this element, how much carbon 12 will be. So we can say .5. Okay. And we can again add the isotope iso_c as written here, lsc underscore custom, the name of the variable that we just created, add isotope iso12c, and an abundance of 0.5, for example, just to show you how different will be. And we can print it again by using G4 cout redirection lsc underscore custom redirection G4 in the end of line. And if we go back to the terminal and we do make, sorry, I mistyped it. So it's add isotope in singular. And if we run it after making again, sorry, I mistake this. This was not allowed. Okay, sorry. I copy pasted the code from before and it didn't work. When creating a custom element, we have to provide the name, the symbol, and the number of isotopes that we are going to add. In this case, we are going to define our custom carbon element by adding 2 isotopes that we just defined before. And we will add them by using the method add isotope with arguments, the name, the variable pointing to the isotope and the abundance, for example, 0.5 each. If we make again, and we run the application, we will see the different output. So the default carbon provided by Geant4, when we didn't specify the isotopes, was made of carbon-12 mostly, almost 99%. When defining our custom carbon element, it automatically recalculated the molar mass, and now the abundance is the one that we specified. Okay, some questions so far? Okay. So the main takeaway here is the units. You have to be careful when using the units, always taking the units from CLHEP namespace and using them accordingly as you have seen here. And in case you are retrieving a quantity from Geant4, you have to keep in mind that Geant4 works in CLHEP units, so you have to divide by this quantity.
But you could give a length in I don't know, grams and a molar mass in kilos per century. Unfortunately, Geant4 will not check these things for you.
Yes. Good point, thank you. Okay. So at this point, we have seen how to create isotopes, how to create custom elements, how to create a default element. We can now jump to creating materials. Again, this is a new class that our project do not know about, so we have to add a new header, include G4 material.hh. And now if we go down here, we can review how to build a material. There are 3 main methods to build a material. If you remember, assuming the atomic number, so it will guess the element, Geant4 will guess the element, and it will take the natural isotopical composition. We can specify the composition of the material by either the mass, specifying the mass fraction, or the stoichiometric numbers by the ratio between different atoms of the material, or we can define a material as a full mix of other G4 material or other elements. We can start here by creating a G4 material out of the custom carbon element that we made. Yes, this is a new class in our project, so we have to include the G4 material.hh header file, where the declaration of this class is. We can also take a look to the file. I was using before the GitHub, but you can also use the install the header file. So in our case, the header files, as I said before, are located in G4 install directory, include Geant4. We can list the files in a directory using ls command. So if we type ls space $symbol G4 install / include / Geant4, you will see all the header files that we have here. We can check if there is a G4 material. There is a G4 material HH in this directory, and we can use gedit to open it, for example. So we type gedit space $symbol G4 install / include / Geant4 / G4 material.hh. And if we type enter, it will open it. Okay. Here you will have some comments explaining what we reviewed with the presentation, how to create a Geant4 material out of a single element from a list of components, either from other materials or pure elements, or from the Geant4 database that we will use later. And if we go here at the very beginning of the class declaration, you can see the Geant4 material constructor with all the parameters that you have to pass. As you see, the state, the temperature, and the pressure have already a predefined value. You can put other value if you want. And then, as in the comments said and as in the presentation, there are different ways of creating a Geant4 material, either by providing an atomic number. So Geant4 will guess what is the corresponding element, or by specifying the elements, the components that will make up this material. Okay, so we can review these two. We will use these two constructors here. Actually, I will keep it open, so you will see how we'll relate one-to-one. So we will start by using this first Geant4 material. We have to implement the name, the atomic number, and the molar mass and density. Okay, so now we go to the bottom. We have already included the Geant4 material.hh, and we can type Geant4 material asterisk mat c equal new Geant4 material. And again, name, atomic number, molar mass, and density. So name, carbon. You can put just that, or you can put a prefix to identify that is a material, not an element. So you can put mat carbon, material carbon, carbon material, as you wish. You can specify an atomic number. So in our case will be 6. We have to specify a molar mass that in our case will be 12 Cl/Hep grams divided by Cl/Hep mole, and a density, which we didn't define before. So we have to define the variable.
Why would A take the units of a molar mass?
It's a convention. You can also use molar. The name, what identifies the molar mass, I think it's a convention. You can use whatever variable name, and still this is not the best practice you can do. Ideally, what you should do is to specify the name of the variable before this step. You should give it a value, and then you simply use it inside the constructor. I am doing this as an intermediate way to keep the code compact. And if you see many of the Geant4 examples, this is what they will be using. And finally, we have to define the density. I don't remember exactly the density, but again, okay. So to define a custom material, a material which is custom, but still we let Geant4 to guess what is the element behind and the isotopical composition. We only have to specify this atomic number and molar mass and density in case we want to change. Okay. However, we can use the other option that existed here it's provided by Geant4 material, which is First, you don't specify what is the atomic number. You simply specify what are the number of components. So we can call it mat custom carbon because it will use the custom carbon element that we defined before. We will give it a name similar to the variable name, just for simplicity. You can choose. But this time we have to use the other constructor. We have to still provide a density, but only the number of components. So density can be the same, doesn't matter. We can copy paste from before. And we can define a new variable for the number of components. In this case, it will be 1 because we didn't have more time to implement more elements, but I think it's clear how, in case you want to declare a material, define a material with more components, you only have to here specify how many, and then use the method add element, and we have to pass this custom carbon element that we just created, like this. And we have to specify also the fraction of it. In this case, it's 100%, but otherwise we will have to specify here the fraction, the mass fraction. Okay. And we can, again, print the materials just to see if there is any difference or not. So we can print out the mat.c. And we can print out the material custom carbon. This was a long shot. Is everyone following so far? Thank you. Okay, so if we go back to the terminal, I will try to keep it small so you can still see the source code. If we go back to the terminal and we type make, it will reveal the application. Amazing, no errors. And if we execute, did everyone compile without errors? Okay. So now we can inspect the output because this is the more interesting part rather than coding. So we have printed out the material carbon. It will print out the density and other properties, and then it will print out the elements it is made of. And we have done the same with the custom carbon, which is using a different isotopical composition. Okay. Yes. So Geant4 will define by itself the element carbon in case we define a material that is being made of carbon, pure carbon. If we don't have, if we, for example, in this case, in this first case, where we only specified the atomic number, but we didn't specify the G4 element that is material made of, Geant4 will create the elements and the isotopes by itself, assuming that the element is made of the isotopes that you can find in nature. If you want a custom isotopical composition, you have to specify by yourself.
1 second, let's just 1 second.
When you defined at the beginning the G4 element carbon with the name carbon,
yes,
I don't know the name by default of the regular carbon.
Yes, then
if it's the same, it may be a conflict.
There should not be a conflict because the Q4 elements and isotopes are identified by an index. Every time you create a new object of the class, the new objects are self-registered, and it will happen with many components of Geant4 that you can assign several times the same name. You should not, because some methods will assume different elements have different names, but nothing prevents you from doing something that is bad. Ideally, you should not do that. You should not create 2 times the same element with the same name, but different composition.
Actually, the definition of this carbon is the same as the default, I guess. Well, I don't know the molar mass, if it's correct.
You mean
there are many things that are defined behind your back, for example.
Yes.
So, because there are other things that are defined, the reason to overwrite or to create something of your own is, number one, educational, so you understand what happens and what is inside one of these things. And the second one is, if eventually you want to create something that has slightly different properties, you're aware of how to do this. However, there are things that are defined that you will find out later in electromagnetic physics, where things are done in a particular way because it was something that came from Geant4.
Yeah, and you were right about the molar mass. I think I put exactly the one that exists in Geant4, but nothing prevents you from saying that your molar mass of element carbon is whatever, and everything will be calculated based on the numbers we provide.
Probably reached or maybe surpassed the stamina of everyone.
Yes, so I think we can leave it here. I'm sorry I could not cover the NIST material database. I hope we can finish it by tomorrow. It will be very easy. This was the tough part, just to show you how granular Geant4 can be. Geant4 in principle allows you to define things with different levels of details, from isotopical composition to simply take whatever is given in nature, the isotopical composition that is found in nature, and you let Geant4 guess and build the element for you. Or even further, you simply call a G4 material, and Geant4 will create the elements and the isotopes for you. Tomorrow we will see even a easier way to define G4 materials, that is retrieving them, and elements, that is retrieving them from an internal database. So all this code that you have been writing down, it was just for educational purposes. In real life, most of the people do not do this unless it is strictly necessary. For example, if you are a nuclear physicist and you want to do a nuclear reaction with a specific target and you want to reproduce some of the effects, maybe you need to do so, or some things like that. But otherwise, you will not need to do that, and you will simply use whatever is given to you. So for tomorrow, we will start by a quiz reviewing the main topics of today. That was a bit chaotic. We will finish with how to retrieve materials, and we will implement the geometry and material list for our application. I don't know if there is any question. There are more questions or not?
1 second.
Yes, I will. Yes, sorry, I forgot. I will upload the coding that we have been using. I think I already copy pasted in the Mattermost. but I will put everything in a zip file so you can check over it, and with instructions with a README how to compile it, and with a bit of comments, some comments. Thank you.
I can always put it in end of day one or some other zip file that is from that directory, and that way you know what it is.
Thank you.
Let's take a look and see if there are any further questions on Mattermost, or no, it seems that everyone is exhausted.
So thank you very much to you, and see you tomorrow. Thank you.
Thank you. Bye.
Thanks. Bye.